Lesson: Predictive Modeling with AI. Predictive modeling with AI has emerged as a critical component in the toolkit of data analytics, allowing organizations to forecast future trends, behaviors, and events based on historical data. This capability significantly enhances decision-making processes, enabling businesses to proactively address potential challenges and seize opportunities with greater precision. To effectively harness the power of predictive modeling, professionals must become adept at utilizing a blend of theoretical knowledge and practical tools, frameworks, and applications that facilitate the development of accurate and reliable predictive models. At the heart of predictive modeling is the ability to identify patterns in data and extrapolate these patterns to predict future outcomes. This is achieved through various machine learning algorithms, each with its unique strengths and applications. For instance, regression analysis is a staple in predictive modeling, often used to predict continuous outcomes. Linear regression, for example, helps in understanding the linear relationship between independent and dependent variables, making it suitable for predicting sales figures based on advertising spend. Meanwhile, logistic regression is employed for binary classification tasks, such as determining whether a customer will renew a subscription based on their usage patterns. In practice, the choice of algorithm is determined by the nature of the data and the prediction task at hand. Decision trees, for example, are highly interpretable and useful for classification tasks, often serving as the foundation for more complex ensemble methods like random forests and gradient boosting machines. These ensemble methods enhance predictive accuracy by aggregating the predictions of multiple decision trees, thus reducing overfitting and improving generalization to new data. A practical example of predictive modeling can be seen in the financial industry, where credit scoring models are used to predict the likelihood of a borrower defaulting on a loan. These models leverage historical data, including credit history, employment status, and other relevant factors, to assign a risk score to potential borrowers. By utilizing machine learning algorithms, such as support vector machines or neural networks, financial institutions can improve the accuracy of their predictions, thereby minimizing risk and optimizing lending strategies. To build effective predictive models, professionals must employ a structured approach that involves several key steps. The process begins with data collection and pre-processing, where raw data is gathered from various sources and cleaned to remove inconsistencies, missing values, and outliers. This step is crucial as the quality of the input data directly impacts the accuracy of the model. Techniques such as data imputation and normalization are commonly used to handle missing and skewed data, respectively. Once the data is prepared, feature selection and engineering come into play. This involves identifying the most relevant variables that contribute to the predictive power of the model and transforming these variables into formats suitable for model training. For example, categorical variables may need to be converted into numerical representations using techniques such as one-hot encoding or ordinal encoding. Feature engineering also encompasses the creation of new features that capture hidden patterns in the data, such as interaction terms or polynomial features. The next step is model selection and training, where professionals choose the appropriate algorithm and fine-tune its parameters to optimize performance. This often involves a process of trial and error, where different algorithms and parameter settings are evaluated using techniques like cross-validation to determine the best performing model. Tools such as scikit-learn and TensorFlow offer comprehensive libraries for implementing and tuning machine learning models, providing practitioners with the flexibility to experiment with various approaches. Model evaluation and validation are critical to ensuring the robustness and reliability of predictive models. Common evaluation metrics include accuracy, precision, recall, and F1 score for classification tasks, and mean squared error, or R squared, for regression tasks. These metrics provide insight into the model's performance, highlighting areas for improvement. It is also essential to validate the model on unseen data to assess its generalization capability, often achieved through techniques like train-test split or k-fold cross-validation. The final step in the predictive modeling process is model deployment and monitoring. Once a model is deemed satisfactory, it is integrated into the organization's decision-making processes, where it can provide real-time predictions and insights. However, the deployment is not the end of the journey. Continuous monitoring is necessary to ensure that the model remains accurate and relevant as new data becomes available. This may involve periodic retraining or updating of the model to accommodate changes in data patterns or business objectives. Despite the technical rigor involved in predictive modeling, the ultimate goal is to derive actionable insights that drive business value. For instance, in the retail industry, predictive models can forecast demand for specific products, enabling companies to optimize inventory levels and reduce waste. Similarly, in healthcare, predictive analytics can identify patients at risk of developing chronic conditions, facilitating early intervention and improving patient outcomes. The implementation of predictive modeling also presents several challenges that professionals must navigate. Data privacy and security are paramount concerns, as the use of personal data requires compliance with regulations such as GDPR and HIPAA. Additionally, the interpretability of complex models, such as deep neural networks, poses a challenge, as stakeholders may require explanations for the model's predictions. Techniques such as SHAPE and LIME have been developed to address these concerns by providing interpretable insights into model behavior. In conclusion, predictive modeling with AI is an indispensable tool in the arsenal of data analytics, offering the potential to transform vast amounts of data into predictive insights that can guide strategic decision-making. By mastering the theoretical foundations and practical applications of predictive modeling, professionals can enhance their proficiency in developing models that not only predict future outcomes, but also provide actionable insights that drive organizational success. The journey from data to decision is complex, yet with the right tools, frameworks, and methodologies, it becomes a navigable path that yields significant rewards.